So if you're here to hear about Android, sorry, I'm not going to talk about that. So I'm going to talk instead about some research I did recently with Chris Valasek, who is not here today because we didn't plan on giving this talk. But we were looking at cars and car hacking, and that's what I'm going to talk about. Before I start, can someone tell me what time this ends? Does anyone have the schedule? Sorry. I'm totally unprepared.
45 minutes.
45 minutes. Okay, great. Okay. Who am I? So you can't really even see the picture. It's a shame. Looks great on my screen. Well, we'll just, I guess, go with it as best we can. I gave the keynote today. Chris works at a company called IOActive. He's in the past done a bunch of Windows heap stuff. What you'll notice out of this is basically that neither of us knows anything about cars or car hacking. We learned a lot while we were doing it, and that's basically what I'm going to tell you guys about. All right, so I'll start talking about what cars we looked at, what an ECU is, and then I'll talk about CAN, which is the protocol for the network in most cars. I'll talk about some protocols that you need to know, and then finally I'll get to the interesting part, which is injecting CAN messages into cars and seeing if you can make them do things. And then I probably won't have time, but you can check out our paper to see how you can do things like get the firmware off of the ECUs and reverse engineer them, stuff like that. Okay. So basically this all started back in 2010. As far as I know. There was a research group made out of researchers from the University of Washington in the United States and University of California, San Diego. And they published a couple of papers. The first one was about exactly what I'm going to talk to you today, like ECUs, CAN buses, that sort of thing, and how you could make the car do things. They got criticized for this, and people were like, well, that's fine, but in order to send these messages, you have to be on the network of the car. And so they wrote a second paper where they showed how they could remotely get onto that network by attacking the car. So they showed a couple ways to do it. One was through the Bluetooth stack of the car. So they were able to send Bluetooth packets to the car that exploited some vulnerability in the Bluetooth stack. Got code running on the telematics unit, and then could send out CAN messages. And then they had another one where you could insert a CD into the car, and it exploited a vulnerability in the MP3 parser and the radio in the car. And then it, again, got code execution and could send CAN messages. So it was pretty awesome research. And that's what got me interested in car hacking. But there was one thing that they did that I didn't like. And that was that they didn't share any information on what they did and how they did it, at least not much. So like if you can't really see this picture very well, but it's a picture that I took from a video that they released where it shows a car, where a car would be, there's this giant black square. Like they didn't even want you to know the kind of car that they were doing research on. So, and then down here, this is an excerpt from the paper. It shows part of a message they would send to do something to the car. They didn't want to include enough information that you could actually do it yourself. So they left out some of the bytes of the message. And to me, this didn't seem useful, right? So I want to be able to do what they did and replicate it and all that stuff. But they thought it was too dangerous to release that information. But I don't think it's too dangerous. I'm going to tell you all this information. And the thing that is sort of funny about this is in this video, where this video is this guy walks across the street. He remotely attacks his car. He has it unlock the doors. He gets in. He has the car start, and he drives off in it. And the first time I was watching it, like it was so alien to me not to release information about your research. I was like, oh my gosh, they're blacking this out because he just stole this car, and the police are going to arrest him or something. But then I realized that it was because they didn't want you to know the kind of car that they were testing on. So that leads to sort of like, why am I doing this? Well, Chris and I are doing this. So basically, we have different cars than they had. It turns out that through various reading all their papers and looking at all their videos, you see enough of the car that you can identify it. It was a Chevy Malibu. So we have 2 cars. So why are we doing this research since it's already done? We have different cars than they had. So 2 different cars. Our cars have more electronics on it, so we can do more sort of interesting stuff. The main reason was because we wanted to release our information to everyone. So we released a paper, like a 100-page paper you can download. It has all the details in it. We released all the tools we used. We released all the data we found. We released even firmware dumps of the ECU. So everything is there on the website, and you can check it out. Because we want other people involved, right? It's like, I don't trust the manufacturers, and I don't trust even just these academic researchers, right? I want it to be where we can all look at our cars and make sure they're safe or not safe and fix it. So again, we give a bunch of examples of everything, and then it was just sort of fun. So that's why we did all this. Yeah, so the first thing is that it was actually like super hard. So the way that I normally, when I want to sit down and I want to hack something, right? This is the normal step I go through because usually I do software. So first thing I do is I download the software and start to look at it, right? So that's usually easy. So getting the target in my normal day of life is quite simple. I just download Adobe Reader or whatever. But when you're doing car research, the first step is to get a car, which isn't so easy. So we had to find a car that was cheap, but had a lot of electronics on it. So the 2 cars that we ended up finding, we basically did a search for the first year, more or less, that all this electronic stuff came out was 2010. So we looked for 2010 cars that had auto park. So this is a feature where the car, like you can pull it next to a parking spot and it'll like parallel park itself. Because we're like, well, if the computer can turn the steering wheel, that's going to be useful because the academic guys never did anything with the steering wheel. So we were like looking everywhere for cars, old cars, 2010 cars that could auto park. And we had all these very interesting conversations with car dealers that were like, yeah, we were looking for 2010, Toyota Prius with auto park. And they're like, oh, what color do you want? Like, we don't care. How many miles, can it have? We don't care. What if it's all scratched up? We don't care. Like, so it was very funny that all the things that a normal person buying a car cared about, we didn't care about. And all we cared about was it could auto park. So we bought it. We bought 2 cars. And when they showed up, they weren't in our town, right? We had to buy them somewhere else and get them shipped to our house. And when they arrived, they had this big checklist that we had to agree to, like, that it hadn't been damaged and that, we agreed. And we were like, we don't care about that. Just make it auto park right now, and then we'll buy it. So at auto park, we're like, there you go. We just signed it. So anyway, it was a different experience than they were used to, for sure. And then when it came time to, I don't know if you can see that. I can't really see it, but it's a picture of a guy sitting. So like working normally for me, I work from home. It's like I'm sitting around in my shorts and typing on my computer. It's quite easy. But working in the car was like difficult. So it would be cold, and you'd have to be out in the car working. It would be hot, and you'd be out in the car working. And it was definitely not as easy as that, because like a lot of times in this picture, I'm like, it's about, I don't know what in Celsius, it's like 0 degrees Celsius or something out, and I'm bundled up in a coat, and I can't turn the car on because it's been hacked and all this stuff. So very uncomfortable. When it came time, when I'm doing my research, usually I attach with a debugger or something, so that's quite easy in software. I just fire up my debugger, Ollie debug or whatever. In a car, it's much harder. I like hurt myself a lot because I don't know how to do mechanic stuff. So we were getting something out, I would have a big gash on my hand. It's like, this is not how computer hacking is supposed to be. I'm not supposed to get bloody while I'm doing computer hacking. Likewise, normally I disassemble programs, reverse engineer them. For me, that's quite easy. I just fire up IDA-Pro. But when it came time to disassemble the cars, that was not easy. So we would have to, so technically, any of the attacks we did, we don't have to disassemble the car at all. But like we would want to take a look at the computer and stuff. So this is the Toyota with the dash removed, and it's a mess. And so we would get the guides that the mechanics use to remove a dashboard, and it would have like 30 easy steps to do it. And I would like remove this clamp, remove this, remove that, and we were like we're not doing that. So we just like get a crowbar and just rip the whole thing off, because we really didn't ever intend to have the cars working at the end. Debugging, pretty easy in your favorite debugger, but in a car, when something's wrong, it's very hard to debug. So this is a thing where I've cut all the wires to a computer, and then I'm trying to wire them back, and it's not working, and I don't know why. And then finally, if you write an exploit or some code and it has a bug in it, it's not that big a deal. You restart the program. Maybe you have to restart your computer. When you do it to the car, you have to call the tow truck, and it's not ideal. So at one point, we did something to the car that overloaded something called the inverter when it wouldn't start. So we had to call the dealer and get it towed there, and it cost us like $4,000 to get the inverter fixed. And then the worst thing was, of course, the dash is all tore out. All the computers are sort of dangling by wires when the dealer sees it, and they're like, well, "What are you doing?" And so it was hard to explain. And also no one blows out their inverter because no one does what we do to the car. So they took them a long time to figure out what was wrong. And they were like, yeah, so Toyota tells us that the first thing we should do is reassemble the car completely. We're like, no, you're not going to do that. That's going to cost like $10,000 because we have all the pieces everywhere. So we said, just make it drive. And eventually they fixed it. But they had to call someone from Japan and Toyota to get them to figure out what was wrong. And then finally, when you're fuzzing or doing something like that, like you want programs to crash. It's like really exciting when things crash. When it's your car and you're doing research, you don't want things to crash. So I actually crashed the car into my garage. I don't know if you can see this picture. It's me, my garage in pieces, basically. So at one point later on, I'll show you how in a Ford Escape you can make the brakes not work. And so I was pulling into my driveway. I was running this particular test where the brakes weren't working. I was being stupid. And my brakes weren't working, not surprisingly, since that's what I was trying to make it do. And then I was pointing right into my garage, and there was nothing else I could do except just keep going. And so I ran into the back of the garage and smashed into, like, this is a bunch of like my tools and stuff. And then here's like my lawnmower got totally destroyed. And this is the back of my garage is now all bowed out. And here's, like, you should never be able to see light coming in through the bottom of your garage, but that's what happened in this case. And then here is another picture. You can see the lawnmower has just been destroyed by my car. But the good news is I did eventually stop. All right, so this is something that the academic guys never did. Here are the cars that we actually did the research on. So the first one, the one that I did most of my work on, was a 2010 Ford Escape. It had things like cruise control, a camera, and then it had, the most important part was this parking assist. Hopefully you guys will be able to see this. So this is a video of parking assist in action. So this is what's supposed to happen. This is how the car works. This isn't like hacking right now. Let me turn it down. There we go. So I put the car into reverse here. I take my hands off the steering wheel. I'm giving it gas to back up. So it's backing up. The computer senses where the other car is and turns the steering wheel. Now it's turning it back the other way. And it's beeping to tell me I'm about to back into something. And then it's done. So it controls the steering wheel. It doesn't control the gears. It doesn't control the acceleration or the braking, only the steering wheel. The other car we looked at was a 2010 Toyota Prius. It had all the electronics you could imagine. So it has something called lane keep assist, which is you're driving down the highway and the car, like maybe you're not paying attention and you're starting to drift out of the lane, it'll automatically adjust the steering wheel to get you back into the lane. So this means, of course, that the computer has to be able to control the car while you're driving fast. It has something called pre-collision system, which is as you're getting ready to, if it senses you're going to crash into somebody, it automatically applies the brakes. And it also tightens up your seatbelt for you. These are all things we're going to figure out how to do in a few minutes. It has intelligent park assist, which is, again, where it'll park for you. Yeah, it's pretty cool. So you could basically drive down the highway without your hands on it, not even paying attention, and you're not going to crash. So that one, and as you'll see when I talk about the attacks later, that the more electronics in the car, the more things that we can do as attackers. So we could do more against the Toyota than the Ford. So we need to talk about these things called ECUs. So ECUs are, it's just a shortcut for electronic control units. These are the computers in the car. So there's, I thought there was maybe one computer in the car, the one that controls the big screen that you might have for navigation. But it turns out there's like 20 computers in your car, 30 maybe. And each one has a very small job to do. So like one computer, all it does is your seat belts. There's one that all it does is your steering. One that all it does is your acceleration or whatever, the engine. So basically all the things are controlled by these ECUs. And these ECUs are just embedded systems. They don't run Linux or Windows or anything like that. They just run some, their own little proprietary operating system. And they're all over the car. And basically they have like sensors wired into them, and then they have other things called actuators wired into them, which are things that it can control. So like, maybe like think about the backup automatic parking thing. It has sensors to sense the location of other cars, and then it has wires that run to physical motors to turn the steering wheel. And then all the ECUs sort of have something like that. And the reason that we can do a lot of things we do is, for a while there was all these computers in the car, and they would run wires to all the computers so they could all talk to each other, right? But they realized that this is silly to run wires everywhere. So instead, they run one bus throughout the car, or one or two or three or something, buses in the car, and all the computers plug into this bus, and they can all communicate on this bus to each other. And this bus is normally for most cars, and it was for our two cars, the CAN bus. So it's kind of hard to see this picture, but this is what one of the computers, one of the ECUs in the car looks like. This is the Ford powertrain control module. So basically all it is, it looks like a ton of wires running into this little box. And if you cut open the actual box, it just looks like a circuit board with like a chip and other things that you might recognize from other circuit boards you've seen. So it's just a bunch of computers, a bunch of embedded devices really inside your car. So I already alluded to this, but the CAN bus is what the bus in most cars that you have for the ECUs to talk to one another. So there's a lot of low-level stuff on how it works. We only cared about the high-level data. So CAN messages have something called a CAN ID, which serves two purposes. One is it's an identifier, of course, and the other one it's like a priority field, so that if two messages are trying to be sent at the same time, the one with the higher priority gets sent and the other one doesn't. The thing that's important from a security perspective is that all the messages are broadcast and there's not any addressing. So any ECU can send any message at once. Every ECU is going to see every message. And there's no way, for me, like if I'm watching traffic, there's no way if I see a message, there's no way for me to know without doing some more investigation which ECU sent it and which ECUs are going to read it. So it's just like packets flying everywhere. And there's also, if you're an ECU and you receive a message, there's no way to know which ECU sent it to you. So you have to, there's like a lot of trust in it. And trust, from security is normally like kind of a bad thing, or it can be. So this is what a message looks like. So CAN messages, so you see here the ID. So in this case, I split into 2 bytes. Chris Valsek. 3B1, so that's the identifier on this one on the top, 03B1. And then the data, the most data that you can send in a CAN message is 8 bytes. So here, there's 8 bytes of data. Likewise, the Toyota Prius, the CAN messages are going to look the same. It's a standard. In this case, the ID is 00B6. The actual data is 4 bytes. You can, on top of, like that's the CAN standard. But inside the data, it can be anything. So like, for example, this 95 in the Toyota Prius message is a checksum, but the Ford never has a checksum on its messages. So this is one of the interesting things you get with our research is you get to see 2 cars. Every car is different. They're all proprietary. All the messages are different. For every car, if you wanted to do our research, you would have to basically redo almost all the work we did. So there are 2 kinds of CAN messages. One is just the messages that normally are sent in the car all the time. Those we call normal CAN messages. The other kind are called diagnostic messages. And these are the kinds of messages that you would never see in your car normally. You would only see them if you had a mechanic working on your car, and the mechanic was using some sort of special tool to query the ECUs or tell the ECUs to do something. So to do that, they use a special kind of message called diagnostic message. And there, the IDs actually sort of mean something. So here you see the ID of the top one is 0760. So that you can actually look up. That is a message intended for the anti-lock braking system ECU. So that is actually something that's standard. And here, and normally CAN messages are just broadcast. You don't really see a lot of back and forth. But with diagnostic examples, you do see like sort of a server-client kind of packet. So here, you send it on 760. The ABS ECU responds back on 68. So that's always the case. It always responds back on 8 more than the ID you sent it from. So you see this back and forth of data. So you get one message going to 60 and 2 responses back on 68. Let's see. Yep, that's it for that. Okay, so let's talk about, like most of this stuff is proprietary, but there are some standards that manufacturers can choose to follow. And both of the cars we looked at followed one standard called ISO-TP. And basically, you might say to yourself when you were seeing CAN messages, like 8 bytes, that's not a lot of data. I'm going to want to send more than that. And ISO-TP allows you to send like arbitrarily amount of data. So the way that it works is basically the first byte of those 8 bytes tells you something about the rest. So if you look at the first nibble, so the first 4 bits, if it's a 0, it means this is the whole thing. If it's a 1, it says this is the first packet in a long message. 2 means it's not the first message. It's one of the later messages. And 3 means it's some sort of like acknowledgement. So I'll show you an example of what that looks like. So in the first one, it's just one single. Everything is in one message. So the very first 4 bits are 0. So it's 0, 3. And the 3 says how many bytes of data there are. So 0, 3 says there's 3 bytes of data. It's all in this message. For a longer message, the first byte, or the first nibble is 1, and then you have 0, 8, 2. That means this is going to be 82 hex bytes of data spread out over a bunch of messages. The message back is a 3, 0, which is like it's like I acknowledge that you're going to send me 82 bytes. And then it starts to send the bytes. So all the rest of the messages are going to start with a 2. And then the next number is like an ordering. So it goes 1, 2, 3, 4, 5, or whatever. So that you can, if they get out of order somehow, you can sort them back. So this is like how ISO-TP works. That's great. That's easy to understand. We release tools to parse out ISO-TP for you. And then so that tells you how to read large amounts of data, but it doesn't say anything about what the data, like the contents of the data. So there is a standard for that as well, ISO 14229 and 230. And this describes what bytes you should send. Again, this is, cars don't have to send these in this format, but they have to at least support it a little bit. So let's look at a few examples of this. So basically, it specifies different types of messages. So one type of message is one called diagnostic session control. So this is, again, if you're like a mechanic, you're going to have to send one of these packets. So here, if you look at the data, it's, and we're going to get to like cool videos of like cars crashing in a minute, so just bear with me for this technical part. So it's ISO-TP, so 02 says it's one message, 2 bytes. And then you got the actual data, which is 1003. 10 means it's a diagnostic session control. 3 is like some argument or parameter for it. And then you get the response back. And the response says adds 40 to the 10 to be that's an acknowledgement. That's always the case. And then it acknowledges that it's a 03 type of action. Okay, so there's other ones, some that are more interesting than others, but this was one that's pretty interesting called security access. So you can't just send a bunch of diagnostic packets to an ECU and have it listen to you. You have to sort of prove that you're who you are. It's the equivalent of sending it a password. The way it works is you send it one of these security access packets, messages. It replies back with 3 bytes. These are just 3 random bytes that it made up. Then you're supposed to, if you're really who you say you are, you're supposed to have a secret that only you and the ECU knows. Using that secret and some sort of proprietary algorithm and these 3 bytes. You plug these 3 bytes, your secret, into this algorithm, and out spits out 3 other bytes. You send those 3 bytes back. It's a challenge response. to the ECU, and if you're right, the ECU does the same calculation. And if you guys both come up with the same response, it says, yes, you have access now. You have security access. If not, it says no. So in this case, we succeeded. And I'll tell you later about how you can get around this as an attacker. But yeah, you'll notice it's kind of weird because you need to have a secret data and you need to have the algorithm. So I'll tell you how to do that. There's some other ones that like initially seem kind of cool. And this one actually we can use. Like these are the types of things you can do. So input-out control is one where it's designed for a mechanic to say, okay, pretend this sensor is reading this value, or pretend that you want to turn the steering wheel or whatever. And so it's ways for the mechanics to sort of make the ECUs do things. And this is, again, so it's ISO-TP is the 6, and then 2F is the type of message in this case, and then some parameters. So when you read the specification, you get very excited. I was excited. I was like, this is going to be so easy. Like, there's these input-out controls to control things. There's things like, read memory, write memory by address. I was like, shoot, this is going to be a cinch. But it turns out that that cars don't have to do all these, and our cars didn't implement almost any of these things that you would want them to implement. So we never got to read memory by address. We never got to write memory by address. And even on the other ones, so like routine control is like an RPC where you make it call a routine. So that sounds really cool. But the problem is like you don't know any of the parameters. You don't know like what the heck it's supposed to do. You don't know anything. And so it's not useful at all. So it was hard. Okay, so that's that. Let's talk about how we actually did stuff. So what tools did we use? And if you wanted to do our work, what tools would you have to go get? So the first thing we got, this is a pretty bad picture, is this cable called the ECOM cable. It's like a couple $100. You can buy it. It basically is, on one end is USB, on the other end is OBD2, which is a connector that every car has to have. So you plug it into your car, plug it into your laptop, and you can start to like read and write CAN traffic that way. We had to make the actual cable to run to your car. I don't know what that ECOM cable is supposed to do, but apparently it's not supposed to plug into your car. So we needed that. It's pretty easy to build. We tell you in the paper how to build it. We needed this little guy called Cardac Plus, at least for the Toyota. It was just something that allowed software on your computer to talk CAN. We got one of these guys. You can get it for like $1. It's just a way it's an adapter to plug into your OBD2 port of your car. So all cars since 1996 have this thing called an OBD2 port, which is used at least in the United States to check that your car has like proper emissions. But it also connects you onto the CAN bus. So then we wrote a bunch of software. So we call it EcomCat. Originally it's written in C. It can do things like read and write CAN traffic. We also generalize this a bit, so to this thing called EcomCat API, which is like this Python interface that allows you to, just with a couple lines of Python, you can read CAN messages, you can write CAN messages. It's pretty cool. So here's an example of how you would do something with the API. So first you open up the device, the ECOM cable device. Then like you can make a message. So here is just exactly like the data that I've been showing you. So here's a message with ID 230 and then some data. And then you can do things like write that message. So here I'm going to write that message as fast as possible for 1 second, 1,000 milliseconds. That's it. In 3 lines of Python, I'm sending a bunch of traffic into my car. It's pretty cool. And then we have a bunch of other functions you can use. Write message from file. So you can have like a bunch of data, a bunch of capture of a bunch of traffic in a file, and it'll just read through there and write it to the bus. Or you can read messages and so forth. Like I said, all this is, we released all the source and everything, so you can download this and play with it. Finally, for let's get to like the interesting stuff. So now I'm going to start talking about how you can inject messages into the car and make it do things. So in our research, we always had physical access to the car. We were always physically plugged into the car. But the academic guys already showed that that's not necessary. You can remotely attack the car and send CAN messages as well. But we didn't do that. There's some things that you can't do. So for example, you can't make the accelerator move at all in the Ford. And the reason is that there's an ECU that does everything by itself. So it has sensors for the gas pedal. It controls the engine. It never listens to the CAN bus for this stuff. So there's no way by just sending CAN messages you can make it do anything. The other problems you'll run into is, like, I might figure out the right message to send to tell the steering wheel to move, but so I'll pretend to be an ECU and I'll send a message that looks like the other ECU's message to turn the steering wheel. But the problem is the other ECU is still in the car and it's still sending messages. So there's sort of a fight between my fake messages and the real messages, and you have to take that into account when you're doing the attack. The other thing is, these car manufacturers, like, they knew that this might happen. So I don't think they knew that they might be attacked. They knew that some of the ECUs might just, like, freak out one day and start sending traffic. So they build safety mechanisms into it, such as, let's see. So there's two ways that the Toyota, you can get the wheel to turn. One is in auto parking. In auto parking, the steering wheel will not turn if you're driving faster than 5 miles an hour and you're in reverse. So that's not that's good safety, not very useful for us. And then when you're driving fast, the lane keep assist thing, it will only turn the wheel 5 degrees. If you tell it to turn the wheel more than 5 degrees, it ignores you. So there's a lot of safety built into the car to make sure that like a random CAN message doesn't make the car crash. Luckily, like, in some cases, we can outsmart these. Well, I guess it's unluckily if you're the driver, but from a attacker's perspective, we can get around that sometimes. So let's start talking about the things that we can do as attackers. So the first thing we can do is we can change the values of the speedometer and other things that on the console. So again, this is what most of our work was just figuring out which CAN IDs correspond to what things in the car. There's like hundreds of these things going on every second. It turns out, like, this is not written down anywhere, it's all proprietary, but it turns out the CAN ID 0201 is the one in the Ford that tells the speedometer how fast to indicate. So if you put in a certain speed value, a certain RPM value into this packet, you will get the speedometer to change. And so this is the Python to do it. So here it's 3 lines of Python will change the output of the speedometer. So here's a video of the speedometer changing.
Alright, so I'm driving down the street. My speedometer says I'm doing 10 miles an hour. So I run my program.
I'm really doing 10 miles an hour.
My speedometer says I'm doing 60, but clearly.
So now it says, you notice a change. Now it's pointing straight up. It says I'm going 60 miles an hour, but I'm not going 60 miles an hour. So you can change.
Okay, program's over.
You can change the speedometer to any value you want. The RPM, the tachometer, you can change as well. Here's the Prius. You can do the same thing. It's a different CAN ID.
Okay.
This is my friend Chris Valsek talking. He's the one who did most of the Toyota work.
Not going anywhere.
So like, the car is not moving.
We're gonna set the speedometer to say we're going 20 miles per hour. And it thinks we're moving.
So you can make that value change to whatever you want. It's pretty cool. Like, that's something that was the very first thing we did. It was pretty easy to figure out which message that was. These other things are much harder. So on the Toyota, if you send this CAN ID, it will apply the brakes. And this is part of the, what we're pretending to do is pretending to get the pre-collision system to work. We're saying, hey, the sensors have indicated that you're about to hit something, and the car's like, okay, I better put on the brakes. This is like what it's supposed to do, but we're going to tell it to do it when it's not supposed to. And so here's the message you would send. Here is the code you have to send. So again, it's like 5 or 6 lines of Python, and that will make the brakes go full force, and they won't let up. So even if you give it full gas, the car won't move because the brakes are fully applied. So here's a video of that. So here we're driving. We're going about 40 miles an hour. I don't know what that is like. And then we're going to make the brakes come on using the computer right now. And so then we're like coming to a stop. So
That's pretty abrupt.
And no matter what you do at that point, you can't drive. It's pretty exciting. So the most scary thing for me was the steering. So I already mentioned that there's safety protections that make it to where you can either only turn 5 degrees, or it only works if you're in reverse and going very slowly, like 5 miles an hour or less. It turns out we figured out a way around that. So what we did, Chris figured this out. What we did was, there's a message that says what gear you're in, and there's a message we already showed you that says how fast you're going. And so we send out a bunch of messages instead of one. We say, hey car, you are going 0 miles an hour. Hey car, you're in reverse. Hey car, turn the steering wheel. And if you do that just right, the car does it. So you trick the car into thinking it passes all the safety checks that it has, and then it will turn the wheel because it thinks it's parallel parking, even though you're driving down the highway. So here's the one, the CAN ID is 0266 to make the steering wheel turn. But you have to also do a bunch of other stuff. So the Python's getting a little more complicated, but still pretty simple. Because we have to send in 3 messages now, all very fast, all right in a row. And here's the video for that. So I was the victim in this one. I'm going to be driving, and Chris is going to make the steering wheel turn while I'm driving. We have a video of this. If you follow me on Twitter, you guys should all be on Twitter, where we had a journalist driving, and I guess he wasn't, I knew it was coming. And the journalist should have known it was coming, but I guess he wasn't as prepared as I was, and we actually literally crashed off the side of the road. But this video isn't quite that exciting, but it was still pretty exciting for me. So I'm driving along, and you watch the steering wheel, so it kind of jerked a little bit. But here I almost went off the road. So that one, I definitely almost crashed. This is the worst one, though, because he catches me right when I'm adjusting my seatbelt. So we literally were off the road at that point. It's pretty frightening. And then here it is if you were driving, what it would look like.
We almost died.
So yeah, it always seems to work right at the worst time. If you looked at that video really carefully, there was a tree, and we were driving and it turned almost right into the tree. So anyway, pretty scary stuff. You can make the acceleration go in the Toyota. This was not quite the same. You can't do this to the OBD2 port. There was a second CAN bus that this packet has to go on, but we could do this. And like it says at the bottom here, it doesn't actually say that here, but it's the next one that says it. So here's the very simple Python to make it do that. The warning here is don't do this at home. And when I say that, you need to listen, because I'm out there making the steering wheel almost crash us. So this is the one where we blew up the inverter. So here is the video of this. It's kind of hard to see what's going on. If you want to grab me afterwards, you can see the video better on my computer. But basically, you'll watch him. Chris is going to pick up his foot from the accelerator, and if you listen, you can hear that the car is still accelerating. In the video, you can actually see the speedometer going up too. So he'll do this twice. He'll be driving, he'll pick up his foot, and the car will still be accelerating quite quickly. Let's see the video. So he's accelerating. Now he picks up his foot. The car is still accelerating. And then he's going to slow down. The engine's still revving it the throttle is down. And then he's going to show, so you can hear the engine still revving. And then the engine won't stop even when you try to turn the car off. And then this is, and that's why it was bad. Still fucking revving. So the bad thing is, about 1 second after we stopped that video, the car went pop, and that was the inverter. So don't do that. But it is scary that you can make the car accelerate and turn the wheel and all that stuff. Okay, so that was all done with normal CAN messages. The next is going to be with diagnostic messages. So the first thing is how the heck do you get around security access? I already mentioned the way it works is you have to be able to take this 3 random bytes and turn it into 3 bytes that the car will accept. So again, this is normally, these are 3 random bytes. It turns out one of the ECUs in the forward was messed up, and it would always send the same 3 bytes, 1, 1, 2, 2, 3, 3. And in that case, it's very easy to know what bytes to send back because you just watch it and you see what it is. Otherwise, it was harder. So the way we did this was we bought the mechanics tools They're just Windows, software, and we reverse engineered them. And the thing that I thought was funny about the Ford tool was the GUI was like straight out of 1988. So I reverse engineered it. This is the algorithm, and we released all this information. So this is the proprietary algorithm. This is what it is. These are all the secret keys for the different ECUs, the different car models. This is for like Ford, Mazda, all sorts of anything that a Ford mechanic would be able to do. And then these are just the secret keys are just 5 random bytes. They don't have to be ASCII, but some of them are. And so I just thought it was fun to see what other people's passwords are. Yeah. So that was my favorite one. So if you watch the movie Hackers, they say like God is the most well-known password. Here, since it was 3 bytes, they couldn't go with God, but they did go with Jesus. So it's close. Anyway, those are some of the secret keys. These are the actual ones for the Ford Escape, the 2010. These are different ECUs and what the secret keys are for them. Same deal with the Toyota. We got the Toyota tool, reverse engineered it. And for us, that was the easiest part because we're software guys. The car part was hard, but reversing the Windows programs, that was easy for us. The Ford tool actually had some anti-debugging built into it, but again, like that's no problem for us. So let's talk about what we can do to the Ford. So the first thing we can do is kill the engine. It turned out there's lots of ways to denial of service a car on the CAN bus. Like that's like super easy. But here is one that works for the Ford. So this tells it to like turn off. I don't know exactly. It's a mechanic thing, but it tells it to like turn off something in the like cylinders or something. I don't know. But anyway, the effect is I'm driving up a hill. The engine's going to die. I'm going to try to start the car. It won't start. And then I start like rolling down the hill backwards. So you hear it just died. So now I'm like put it in neutral, trying to start it. My son is filming this, by the way.
Did you kill the engine?
What do you think?
Yeah.
So anyway, you can kill the engine. It won't start. You've disabled the car. You can turn the lights on and off. Like the headlights, again, it's just a certain CAN message you send it. I would show you a video of that, but we were planning on filming that video right after we blew out the inverter and the car wouldn't start anymore. So you'll have to wait for the video for that. But trust me, we can do it. Same sort of deal with the Ford. You can send this CAN message, and all the lights will turn off, and a lot of other stuff too. So here's a video of that.
I'm about to DOS the smart junction box.
So the headlights turn off
immediately.
And then
not too long after, I lose a lot of other stuff. So the radio, temperature, air conditioning.
So the radio, air conditioning, none of that stuff works.
Like no longer, nothing happens. The
Inside lights
come on,
don't work.
No matter what you do. Brakes don't work, or the brakes work, but the brake lights don't work. And you can't get out of park, so you're stuck in park.
Yeah, so you can't even like physically move the gear lever out of park anymore. And the scariest part, like I mentioned quickly, was the brake lights don't work either. So you can apply the brakes, but no one knows you're applying the brakes, which you can imagine can be dangerous. You can make the horn turn on for as long as you want. Even if you turn off the car, the horn will still be on. So we did this with Andy Greenberg, who's a Forbes reporter.
Oh my God.
So.
What happens if I can't do anything about this?
So we could do it as long as we wanted. It's pretty annoying. We can make the seatbelt turn on or tighten because like it thinks it's going to be an accident. So here is again me as the victim as Chris keeps tightening my seatbelt on me. So it's not going to kill me. It's not dangerous in itself, but it's definitely like a distraction when you're driving. It's like if I was just getting ready to jerk your steering wheel, I would do this, and you'd be like, what the hell? And then I would jerk your steering wheel. That would be my attack if I was a bad guy. You can lock and unlock the car doors in the Toyota. Again, this was one we planned on filming after we blew up the car. So you don't get a video, but we can do it. You can change the fuel gauge. So here, the car doesn't have much fuel in real life, but we just told it it's full. So this, you can imagine, like, if you just made it full all the time, you could trick your friend into, like, thinking his car had fuel. But it's like, wow, this Prius really does get really good gas mileage. And then one day it's out of gas. And then here is, like, the big one, I think. So and the Ford, you can make the brakes turn off. And then we're gonna be out of time. So I think that'll pretty much be the end of the talk. The way this works is you can basically make the brakes bleed. There are safety precautions built in where it only works if you're driving like 5 miles an hour or slower. But it turns out that even when you're driving 5 miles an hour or slower, you eventually want to stop. But with this, you can make it to where you can't stop. So here's a video of that. Chris is the victim this time, and he's going to try to park. I'm gonna make the attack go automatically as soon as he gets slow enough for it to work. And then you'll hear, this is what surprised him. You'll hear the car make this really horrible noise because the brakes are bleeding and the brakes aren't going to be working, and he won't be able to stop. So let's see.
I found a spot.
So he's just going to park here.
All right.
So that's the noise. That means the brakes aren't working. Now he's driven up in the curb into the grass, and no matter what, he's like jamming on the brakes and they don't work. The only reason I was going to make him drive all the way into the trees, but if you notice, he's jamming the brakes so hard he actually knocked the cable out that I was controlling the car with. So he was able to stop the car only because of a physical limitation. So we're going to skip this part, but check out our paper. It has all the things about how to get the firmware and reverse engineer it. One more quick thing I'd like to show you is you can actually reprogram the firmware so that you don't need to be plugged in. You can be plugged in for a second, reprogram it, and then you're done. So this is how quickly you can reprogram it. So, okay, reprogrammed already. Now I'm not plugged in anymore, but I'm still controlling the ECUs. See, I'm driving along.
Your backwards camera's still on because.
And I make the backwards camera stay on even though I'm not going backwards.
Programmed to keep sending that packet, even though I'm no longer connected to the OBD2 port.
So you can reprogram the ECUs. So if I just have access to your car for like 10 seconds, I can do that. So you can. I talk about ways in the paper on how you can detect attacks, but I'm out of time. Check out the paper and you can see it. So the end is that you can control a bunch of stuff in your car. The more electronics you have in the car, the more fun things that an attacker can possibly do. We released everything, and the reason we did that is we want everyone to be able to, do this research and for themselves and see what it's all about, and just check out the paper. So that's it. Thanks.